Yes, dear children, let us start revising D block elements. Okay. Now, D block elements are also called as transition elements. You know it very well. And what is the placement of D block elements? It is between S and P. Is it not? First and second group, they are S block elements. And from 13 to 18, they are P block elements. And in between the two, you have between 3 and 12, they are D block elements. And the general electronic configuration is N-1 D 1 to 10, NS 1 to 2. So here, when you want to write the configuration of chromium, that is 24, that time, in order to make the D orbital half filled, you will take one electron from S and put it in D. So you will have 3D5. Okay, so we will see all this one by one. Now, how do you define transition elements? Transition elements are those which have partially filled d orbitals either in the atomic state or in their common oxidation state. Okay, say for example, if you are considering copper. Now, in the case of copper, it is having an atomic number 29, and in the case of zinc, which is having atomic number 30, you will find that this is 3D10 4s2. In the case of 29, you may be writing it as 3D9 4s2, but then again, in order to make the d orbital fully filled, what we do? We make it as 3D10 4s1. This is how you write. Now, this is quite familiar to you. You have studied in 11th class very well, right? Now, this Cu is also having completely filled d orbital. Zinc is also having completely filled d orbital, right? But then, if you consider Cu plus, then this 4s will be lost. Again, it will be having 3d10. But if you consider Cu2 plus, then one electron from 4s and one electron from 3d will be lost. And so, this Cu2 plus will have 3d9 configuration. But then, zinc, which is existing in 2 plus state more commonly, this will have again 3d10 only. Zinc 2 plus will have 3d10. But Cu2 plus has 3d9. Now, what is the definition telling? Transition elements are those which have partially filled d orbitals either in the atomic state or in their common oxidation state. Now, common oxidation state in the case of Cu2 plus, it is having partially filled. It is not fully filled. But this zinc in its common oxidation state, it is having fully filled 3D. Is that clear? So, if it is having fully filled 3D, then it is not considered as a transition element. But copper is considered as a transition element. That is why it is given. Zinc, cadmium, mercury are not regarded as transition elements because of fully filled d orbitals in their atomic state as well as in their common oxidation state. Okay. So, what is the zinc, cadmium, mercury? You have atomic number 30 zinc, then below that you have cadmium, and then below that you have mercury. All three of them are not regarded as transition elements. Now, what do you have in the first series? First series is 3D series, which is ranging between atomic number 21 to 30. 4D series is between 39 to 40A. 5D series is lanthanum, which is having an atomic number 57, and between 58 to 71, it is not placed here. It is placed separately as F block elements, and 57 is then followed by hafnium, whose atomic number is 72 to 80. So this is your 5D series. Then 6D series, again you have actinium, which is 89, and again between 90 to 103. You are not having here, and they are placed as F block elements below lanthanoids. Elements following lanthanum are called lanthanoids. Elements following actinium are called actinoids. They are not placed in this series. So that is 104 to 112. That is coppernicum. Rutherfordium to coppernicum. Right? Now, what happens to atomic size across the period? Now, atomic number is increasing. So, with increase in atomic number, atomic size decreases. This you have studied. Across the period, the size decreases. Okay. So, with increase in atomic number is nothing but nuclear charge. But the decrease in atomic size is small after midway. After midway का मतलब क्या है? That is, say after chromium, manganese and iron. You will find that the decrease in size is smaller. Initially it may be a little significant, but later on it will be smaller. Why it is smaller? Because after the half-filled state, once the d orbital gets 5 electrons, the next d electron shields the outer electron. So, because of the increased screening effect, what happens? It is counterbalancing the increased nuclear charge. So, the size remains almost the same. Okay? You know very well that screening effect of d and f orbital is poor. Now, suddenly when you find zinc, you will find that the atomic size again increasing. In the case of zinc. Why? Because it is having 3d10 configuration. So, because of electron-electron repulsions in the same orbital, the size of zinc will be great. Okay? So, this you have to remember. Why is the size remaining almost similar after midway, and all of a sudden in the case of zinc, why it is increasing? Now, the radii of 5D series are almost the same. 5D means you have this lanthanum 57, then followed by hafnium to mercury. This is called as 5D series. And in this series, you will find the radii is almost the same as those of the 4D series. 4D series की और 5D series की दोनों की atomic size almost similar होता है. Why? Now what happens? Now after 57 you have 58 to 71. Now 58 to 71 I told you they are placed as F block elements. Right? So the effect of screening effect, it is poor. Why? Because in 58 to 71 it is 4F that is getting filled. Okay. So this 4F will show very poor screening effect. Very poor screening effect की वजह से क्या होता है? The outer electrons will experience the nuclear attraction. So the filling of 4F before 5D, it results in a regular decrease in atomic radii. Okay, and this is what you call it as lanthanoid contraction, and this compensates for the expected increase in atomic size with atomic number. So what is the net result? The net result is lanthanoid contraction. Okay, and because of lanthanoid contraction, the second and the third series, they exhibit similar radii. So this is a very common question that is asked. Why zirconium and hafnium have similar atomic radii? It is due to lanthanoid contraction, right?